Hi everyone, I am Selena and this is the course project of EEE414 Introduction to CMOS VLSI Design. For the course project, an 8 to 4 SRAM array was designed where the memory arrays will be two-folded. There should be 16 words and each word should be consisting of 2 bits. The 3 to 8 row decoder designed in the first part of the project selects between 8 rows. However, in the two-folded 8 to 4 SRAM design, there will be an additional address bit which is connected to the column circuitry, and this additional address bit will be used to control the bit selection. Also, there are some additional inputs given to our system, like S1 bar signal given to the system acts as the write enable. The data S1 and data S1 bar signals correspond to the bits that are written to the SRAM cells. Additionally, the write 0Q1 and write 1Q1 inputs are included in the system as the inputs of the CMOS transistors in order to account for the charging conditions of the bit lines that are included in the system. And importantly, the clocks that are included in the overall system are phi 1 and phi 2 bar. The system works by using overlapping clocks, which means that non-overlapping clock logic is not implemented in our system, so that these two clock inputs are the same as each other and they are connected to the same pulse voltage source. The reason behind these clocks being equal to each other is that phi 2 bar becomes the twice inverted version of phi 1. And this is the schematic of the SRAM design with bit line conditioning, column circuitry, and memory cells. And this is the inner part of the SRAM cell, and it's SRAM memory cells, and they are the transistor sizes. The SRAM cells consist of an array of memory cells along with the row and column circuitry. The 6 transistor SRAM cell is shown here, and the pull-up transistors are weak, the pull-down transistors in the cross-coupled inverters are the strongest, and the excess transistors are of the intermediate strength. So the transistors of the SRAM cells are sized in order to maintain the read and write stability. And now let's move on the SRAM design with cables. So this is the schematic of the SRAM cell that we have designed in our project, and here is the tin cell layout version of the previous schematic that we have shown for the SRAM cell, SRAM memory cell. And this is the overall SRAM array schematic design. So here is the bit line circuitry, here is the column circuitry, and there are the SRAM memory cells. And this is the layout run for the SRAM arrays. Later on, we merged the project part 1, which includes 3 to 8 decoder and clock qualification circuitry, and the second part of the project, which includes bitline conditioning circuitry, column circuitry, and SRAM array cells. So we merged these two and finalized our project design, SRAM design. So this is the block connections of the first and second parts of the project for SRAM design. And this is the overall layout design of the first and second parts of the project. Here is the 3 to 8 decoder, and here is the clock qualification circuitry, which is connected to the SRAM arrays and bitline conditioning and column circuitry part. And here are the NOR gates that we have used for input qualification.
Hello everyone, my name is Ecem Şimşek, and now I will continue our presentation with the section of pre-layout simulations. Now in this figure, we can first of all see the test bench schematic simulated for the input condition of data S10 and data S11 being equal to each other, writing to and reading from the given addresses of 1111, 100, 00111, and 000. And here, as we can see, in accordance with the clock cycles, we can read the data that we write to the given address bits as long as we are staying in the same address bits. And also we can see that here we are not getting a continuous line for the data that we are reading, because our system only works at periods where clock is equal to 1. So it doesn't work at the parts where the clock is equal to 0. And now here we can see the testband schematic simulated for the input condition of now data S10 and the inverted data S11 as compared to the previous inputs. And we are again using the same address bits that we have used before. And again, we can see that we are correctly reading and writing. And now we can move on to post-layout simulations. Post-layout simulations refer to the period where we actually combine the results coming from the layout and the results coming from the schematic. And also in the post-layout simulations, we include the extracted parasitic resistances and capacitances. So we can consider post-layout simulations more close to the real-life case of actually implementing an SRAM design. So here we can see that the config testbench schematic simulated for the input condition of data S10 and data S11 being equal to each other. And we can see that we get the same results that we have gotten from the pre-layout simulation. So this shows that our system here works correctly. And here we can see the config testbench schematic simulated for the input condition of data S10 and inverted data S11. And we can again see that these results are the same as the results we have obtained for the pre-layout simulation. So this again shows that our system works correctly here. And now we can move on to another condition. So in the previous simulations for both pre-layout and post-layout conditions, our clock period was equal to 10 nanoseconds, and our system was working correctly for this clock period. And then we performed some tests in order to see the minimum clock period at which our system continues to work. And so we decreased our clock period from 10 nanoseconds to 5 nanoseconds. And we have observed that at 5 nanoseconds, there are some problems with our read and write operations. We are getting some incorrect output results for the clock input with period of 5 nanoseconds, so that we can say the minimum clock period of our system is not exactly 5 nanoseconds because we get incorrect output results at this frequency, but it is very close to 5 nanoseconds. And then for both pre-layout and post-layout conditions, we performed bit line precharging. And here we can see the phi1 and bit 0 voltage waveforms plotted for pre-layout simulations, along with the marked data points for calculations. And here we can see that as phi1 is falling, the bit 0 bit line waveform is rising, so that we will be looking at these differences between them. And since here we have a rising condition, we will be calculating the rising propagation delay. And for the pre-layout case, we calculate this bit line precharging rising propagation delay as 404.7 picoseconds. So it is very small. And for the case of post-layout bit line precharging rising propagation delay, we are measuring it as 983.5 picoseconds. And this concludes our work for the bit line precharging measurements. And now we can look at the post-layout write delay. So here we can see that we took the write delay measurements for the cases of writing 1 when the bit cell contains 0 and writing 0 when the bit cell contains 1. So as we can see here, the first waveform here corresponds to phi1, which is our clock. And then we have some bit line waveforms, which shows the difference between these two conditions. And here we can see that the difference between their averages will be very small. It will be approximately 1 nanoseconds. So this means that our write delay is close to 1 nanoseconds. And we also performed post-layout read delay. And here in this case, we measured the read delay for reading 0 case. And here we took the difference between the time points of phi1 and the time points of a bit line here. And then in the next measurements, we are measuring the read delay for the condition of reading 1. And here again, we see that although their voltage points are at 2.5 volts, which is VDD over 2, we can see that there is a slight difference between their time points. So again, we take their difference. And when we average these two differences, we get the read delay measurement. And just like the write delay case, it is very close to 1 nanoseconds. And now we can talk a little bit about post-layout power optimization, because it is an important constraint of our system. So first of all, we simulated our system with VDD equal to 5 volts case, which is figure 21 here. And here our current was equal to 13.16 milliamperes. And since we already know the voltage value, we can calculate the power value very easily by simply multiplying them. And it gives us 65.8 milliwatts. And also, we can calculate the case where VDD is equal to 4.95 volts. And here, 4.95 volts is the case where our system works. This is the minimum VDD value. And here, the power value is 63.61 milliwatts. So here we can see that we have approximately an improvement in the power consumption of our system of 3.33%. And this concluded our work for our SRAM design. Thank you so much for watching our presentation.